Folks, uh, here we go, Monday the 7th of December. Today what we get to do is we get to talk through sliding. So sliding isn't necessarily something that's crazy new to us, but the nice thing about sliding is that this is definitely something that we've experienced in real life, right? Whether you're the dog in the lower left corner picture, or you're the bus in the top right picture where you're just sliding across the ice and or a slippery surface and just rolling through stuff. Okay. So couple things for us. So right now, what you've seen is left side of this, meaning that you've seen all these different formulas and you want to make sure that again you have those written down. Now, I will likely start to have the cosine here of theta disappear a little bit more, just because if we're on an angle, I'll be very specific and very explicit about that so that you know that we're on an angle. Otherwise, on the right side here, now we start to see kinematics back again. Kinematics become kind of crucial for us, especially for some of the problems we want to run here. Okay. All right. So you've seen this slide now. I think this is the third time. All right. We've done the first one or the second part, right, where we've had an applied force, F1 equals force applied minus the force of friction. We'll see another one of those today. Okay. For the most part, we dealt with those pretty well. No unbalanced force, meaning that the object is either not moving or just barely starting to move, or the weird one that sometimes we forget about, no acceleration. It's moving at a constant speed. Right? Set to cruise control, blah, blah, blah. There you go. The no applied force one on the top, now this is the new one for us. Right? And the reason that this is really the new one for us is because up until this point, we've talked about find the acceleration or the coefficient of friction, which is a nice problem, but the applications of those two aren't really extensive. So that's where we're going to start and begin to look at that type of problem again there. Okay. So here we go. So you, a 75 kilogram, get running really fast so that you're traveling at 7 meters per second, so about 15 miles an hour. And then you jump smoothly and slide across a frozen lake. If you travel 18 meters before you stop, what is the coefficient of kinetic friction between your shoes and the ice? Now, the crazy thing about this problem is that we can actually do this thing. Well, maybe not yet. I don't know how thick the ice is yet, at least in this area. But you've probably experienced this at some point or another. Walking on the sidewalk, and all of a sudden up ahead, you see that little bit of ice across the sidewalk for a ways. So, as a kid or a 42-year-old grown man, I've done this too, where I've seen that thing and gone ahead and just taken off and slid across it, right? You've also probably slid across your hardwood floors or kitchen floors in your stocking feet. I mean, in your socks. Sorry, such a Wisconsin thing, right? So this is actually something that we've done. So, okay. All right. So first and foremost, the big thing we want to know is these two preliminary questions. We want to know, is there an applied force and is there a frictional force? For us, the second question is always true because now, if you look at this thing, we are looking for the coefficient of kinetic friction. Because we're looking for that, we know there has to be a frictional force. Okay. All right. So go small. We want to find our coefficient of kinetic friction. We know the initial velocity is 7. We know our final velocity is 0 because we stopped, right? We know our distance is 18, and we know our mass is 75 kilograms. Okay, so we start off with a couple things. So when we look at this thing here, we see it's a sliding problem, so our applied force is 0. Hey, buddy, you can come say hi. Oh, look at that baby. Yes, okay, all right, come on, I gotta teach you. Our force applied is 0. Come on, get out of here. Here you go. Yeah, I know you just woke up. Force of friction is the fun. So friction is what is causing us to have this acceleration here, meaning that once you slide across the ice, there is no more applied force because you're not actually reaching down and pushing with your hands or trying to push with your feet or anything like that. You're just straight up sliding. So because of that, our friction is our fun. Okay? It just happens to be a negative acceleration for us. Right? So to find mu, okay, we need to find a few other things first. We got to find our force of friction. Okay, we got to find our applied force, we got to find the fun, and we have to find the acceleration. Now, as you look through these, hopefully you're starting to generate ideas on how to solve these things. Remember, our force of friction, UMG. Okay, our force applied, we'll talk about that in a second, but that's a specific number for this case. Our fun, MA. And then acceleration, we've got a bunch of numbers over there that we can do kinematics with. So now we just have to figure out which one's the best one, right? So for us, even just talking through those kind of concepts, we should see that we can't start with a force of friction. We actually have to start at the bottom and work our way up the list, okay? So when we look at our formula here, this is the one that we always start with. Fun equals our force applied minus our force of friction. At least for this chapter, that's what we're starting with, right? Remember, we said our applied is 0. There's no way that we can apply a force here. Once we start to slide and we travel at 18 meters, our applied force is 0 because we're not moving it forward at all on our own accord. It's all based on that initial momentum that we have created. Okay? So in this case, our fun equals our negative force of friction. All right, well, if that's the overarching piece for us, then we can find 2 of the 3 things that we want to find, right? We can find our fun, we can find our friction. Once we know our friction, then we know our coefficient of static or of kinetic friction, right? So in order to find acceleration, we're going to use this equation. We've got an initial velocity, right? So because we've got initial, because we've got a final, because we've got a distance, the best one for us is this VF squared, right? Yeah, we could use fun equals mile, but we don't know fun yet, okay? So once we get to this stage, notice I subtracted over the 7 squared, which was negative 49. 2 times 18 is 36. Take 49 divided by 36, right? So if I go here and basically say, all right, that's divided by 36, right? My acceleration is negative 1.36 meters per second squared. Now, hold on a second. Is that right? Should it be negative or should it be positive? Well, remember, we're starting at 7, ending at 0. So we're slowing down. So it should be negative, okay? So now that we know the acceleration, what we can do is we can find our fun. Because remember, fun equals our negative force of friction. So fun is going to be this 75 kilograms, again, the mass down here, right, times our acceleration, or in this case, deceleration, right? So we find that our unbalanced force is a negative 102 newtons. Now, what is that unbalanced force from? Well, it's from slowing down and stopping eventually, right? So it's from friction, okay? So because that's from friction, we know that's negative 102, right? So this equals mu k mg, right? Again, notice I got rid of the cosine. Why? Because this ice is horizontal. Okay? Now, if it were to be an angle, then we got a whole different set of circumstances that we're looking at, which we'll talk about tomorrow. Okay? So we take our mass of 75 times our g. Again, because we're looking at normal force, it's going to be positive, right? So that's 735. So negative 102 divided by negative 735 gives us a mu k of 0.9. Now, big point of emphasis here, this thing needs to be positive. If it's negative, that means it's actually so slippery that it's speeding it up, theoretically, right? So for us, this is what we end up seeing, how fast or how kind of sticky or grippy this ice would be. Okay. I know it's not tremendously different. The big change in this one was using the kinematics to actually find our acceleration. That's the big difference that we haven't done before yet. Okay. All right. Pushing now. Pushing. Okay. So check this one out quick. All right. So we got to push a 40 kilogram desk that's resting on carpeted floor. The coefficient of kinetic friction between the desk and carpet is 0.55. How hard do you have to push on the desk to get it to accelerate horizontally at 0.2 meters per second? So we ask immediately, is there an applied force? Yeah, right? The way that we know there's an applied force is you push. You are the applied force, right? On the previous one, we didn't talk about us pushing or the car pushing or the whatever pushing, right? So this one, for sure, there's an applied force. Is there a frictional force? Absolutely. We got a coefficient of kinetic friction right there. Okay? So here's what we see. we got the mass of 40, we got a coefficient of kinetic friction of 0.55, and acceleration of 0.2. All right. So here's the big picture piece of all this, right? The applied force has to be big enough to counteract friction and accelerate the desk. So what we have here is we have to have the ability to get this thing first to move. Once we get it to move, then we have to get it to speed up, right? Think of pushing a box and all of a sudden it's super heavy. So you have to kind of, roll up your sleeves, so to speak, and you dig in a little bit more and really start to push. Once you do that, then you start to accelerate it, okay? So for us, this is the amount of force we have to figure out. We have to figure out how to get it going and then how to get it going faster, right? So we need the force of friction and we need the fun, right? Oops, sorry. So because we need the force of friction, because we need the fun, the force of friction is to get it started. The fun is to actually get it to speed up and go faster, right? So our force of friction, mu mg, right? So if we know our m from over here, and we know our mu from there, right? Gravity is just gravity. So our force of friction here is 215.6. That's just to barely get it to move, right? So that's just pushing on it, and now it just starts to move a little bit, okay? The fun, this is actually to get it accelerating, is going to be the mass again, but this time the acceleration. Now, a way we would twist this problem, give you a distance, give you a final velocity, tell you, hey, you got to go in this fast over this much distance or over this much time, right? That's a way that we can make this one a little bit more difficult, right? So in this case, our fun is 8 newtons, right? That's just the amount to get it to accelerate that 0.2 meters per second. That's all it is, okay? Now, what we have to do, remember, is we have to use both of those, because the force of friction is how much force we need just to get it started. The fun is how much force we need to accelerate it. So separately, those are nice, but for us, we need them both together. So we look at this. Our fun equals our applied minus our force of friction. So 8 newtons is our fun, 215.6 is our friction. So we add those two together. Add over the 215.6. Our applied force here needs to be 223.6 newtons. Those two together will get us to start this moving and then accelerate it on and keep it going. Okay. All right. Try these out. So what you're going to do is you are going to actually pause this video and go ahead and run this thing now. Okay. While you pause it, I'm going to take a drink of coffee. Here's how you should run this thing. Okay. So for the first one, it says determine an acceleration of a 45 kilogram crate if we push it horizontally with a force of 615 newtons. Look at that. You push horizontally. That is your applied force, right? So because we have a mass of 45 kilograms, and now we also see the kinetic friction of 0.175, what we're able to say is, okay, I pushed with that much, right? Friction caused this much because that's mu mg, right? So if I want to find the acceleration, I got to find the fun then, right? Well, if I've got my applied and I just calculated my force of friction, meaning that those are the two things that I need to do in order to find fun, then my fun is just the difference between those two, 615 minus 77.2. So that's 538 newtons, right? So, I suppose I could use kinematics, but I don't have enough information there. I don't have a distance. I don't have a time. I don't have a final velocity, right? I know the initial 0, but other than that, I don't know anything, right? So once I now start to see, okay, I'm still going to use that, fun equals applied minus my force of friction. It's just in this case, they gave me my applied and then I just found my force of friction, right? So to solve this, my fun equals ma, So I took my 537.8 divided by 45. I found that my acceleration is 11.95 meters per second squared. Okay? That thing's moving quick. After a second, you're going about 23, 24 miles. Or no, I'm sorry, 45 miles an hour, I think. Wait, no. Yeah, I think it's 25. Anyway, all right, that's the first one. Second one, calculate the coefficient of kinetic friction between a concrete floor and a 0.185 kilogram hockey puck if it takes 35 meters to slide to a stop when the puck starts out at 41 meters per second. All right, so we want to find mu k, right? So I've already rearranged my formula. So fun equals my applied minus my force of friction. Because there is no applied friction, because we are, I don't know if you see that or not, because we're sliding, right? Then we know that our applied friction is, or our applied force is 0. All right. Now, I don't necessarily like jumping at this one right here, but I'll explain what that means. Right. So we want to find our acceleration because that's going to give us our fun. Okay. So our initial velocity is 41 meters per second. Our final velocity is 0. Our distance is 35. Now, in this one, you can see I went ahead and calculated the normal force. All right. The normal force is a nice calculation, and it basically just ends up showing up down here. Okay. When we take our fun and everything like that. Right. So please don't freak out about that. And if you want to, you can completely disregard this equation over here because it really doesn't. Okay. So once we know our normal force, that's nice, that's helpful, that's great, right? To find A, we use our VF squared, right? V squared, VI squared plus 2A delta D, right? 41 squared gets moved over. Divide that by 70, you get a negative 24 meters per second squared. Again, why is it negative? Slowing down to a stop, right? Decelerate. Okay? So then our fun is 0.185 times negative 24. So it's negative 4.44 newton, right? Okay. Again, that unbalanced force is all due to friction. Why is it negative? Because friction is acting the opposite direction that we want to. We want to continue sliding forward, right? And if there wasn't any friction, guess what? We would. But because there's friction, we can't. We have to eventually slow down and eventually stop, right? Excuse me. So then this thing just goes right in there. Our normal force came from right up here, just mu mg. Do you have to calculate the normal force first? Only if I ask for the normal force first, which I don't anticipate I will do it at least right now. Okay. So once we take these two, we take 4.4. Sorry, I should have a negative. I should have a negative. I got a little sloppy there and getting rid of them, right? My mu is equal to 2.45, right? That concrete floor is pretty darn sticky, pretty darn grabby, right? Between the combination of the two, we get it to slow down pretty quick. All right. Section 2 has a bunch of great homework questions on it. I would definitely encourage you to look through, I believe it's 3 and 4, and see whether or not the car actually hits the tree on the highway. Okay. That's all I got for you today. Take care. Let me know if you got questions. Tomorrow we start talking angles. All right. See ya.